Here we go. I've posted the lab sheets for Kinetics, so if you click on next week's lab, there's two things there. You can upload your Excel activity when that's done into there, and it's not going to get graded until I go through and manually grade them. So it'll show up as 0 even if you've submitted that. And then I changed the color to blue for the stuff that is procedure notes for in-lab. There's still the pre-lab quiz that's going to come up, and that's based on doing it in person. So it's, I think, 10 points. It's pretty tough. The post-lab will be 45 points. And then, here's the Kinetics lab manual, and that is a PDF from the overall manual, so the pages show where it fell in the lab manual I'm working from. And then I gave an Excel version of the table so that you can start out with a table that's pre-formatted. So it's got all the borders and stuff. And that's just a resource for you to use to try and make a beautiful lab report. Oh yeah, we were on page 23 and example 3, and I popped that into Excel yesterday. So do you remember how that came out? We found that the 1/over concentration versus time was linear. So what does that mean?
That's a second order.
Yeah. So on this one, example 3, we graphed it yesterday and we found that this one was linear. And that means that it is second order. So our equation is 1/a time t equals kt plus 1/a naught. So we can write the rate law. There's only one reactant. So there's our rate law. And we've got some data, so we want to determine the half-life. And is it constant or close to constant? Which order has a constant half-life? Yeah, first order. I kind of think of that as normal, right? First order is what we think of as a little bit like normal, like radioactive decay. When we talk about the half-life of cesium, for example, is constant. It's a value that's constant, and we hear that in the news after the Fukushima meltdown, for example. So the other order, 0 order and second order, have half-lives that vary in time, and the half-life for the 0 order gets shorter and shorter, right? Because that initial concentration is in the numerator, and as that goes down, the half-life goes down. For the second order, the half-life has the initial concentration in the denominator. So as that goes down, the half-life goes up. So when you think about second order and reacting away, we're looking at two things having a collision coming together. And as that concentration goes down, it takes longer and longer for them to find each other. Mm-hmm. So we are going to find that the T1/2 gets longer for second order reactions. That's RXN reactions. All right, so find that K and that half-life. So for second order, T1/2 is, so I'll provide you with those equations, but you could also derive them if you needed to. Takes a little more time. All right, and then we had our graph. Oh, I didn't write down those values, but we can calculate the slope manually. So let me modify this data. We're going to look at 1/NO2, and that's what we found was linear. So that value, 48.82, 51.475. Right, so I'm just taking the value of concentration and taking 1 over that. So you can do this with a calculator in your hand. You don't have to have Excel. We use Excel to determine that it was second order, but from that point, you can just calculate what you need. And then we'll do a slope between those 2 points. Oh, well, this is 10, 1 over 0.1. Oh, and this is 212.76. Okay, cool. I'm not sure. I jotted down some values, and they were not clearly marked. 212 point, what's that value? 76 minus 10. Because up here, our initial, I was taking the difference in the 2 points. Just the rise over run for that slope. And then what did I get? I got 10.1 for my constant. And then the half-life. That initial concentration. Yeah, we don't have a lot of digits there. Yeah, I would round to 0.99. All right, so collision theory. Have you guys considered collision theory before? Do we see this earlier, maybe in gas law?
Yeah.
A lot. Okay.
Yeah.
Well, there are a couple of things that affect how fast a reaction can happen. And there's two main effects. They have to have a collision, so they have to be able to find each other. They have to have enough energy in that collision to break a bond so that the atoms can rearrange. And they have to have the correct orientation so that when they have that energy and they break a bond, that the products form instead of the reactants just forming again. In general, our rate constants increase with temperature. So why would that be? Two things that we need.
More collisions over time.
Yes, but why? Yeah, so at a higher temperature, how does that affect the speed of molecules? Yeah, molecules are moving faster. And so how does that affect the rate? How does that affect their collisions?
Does it increase the probability of them bouncing off of whatever container they're in or each other?
Yeah, okay, so they have more collisions because they find each other fast. They're moving faster, right? So there's like in person, we might do a little demo. We might like go out in the hall or find a space and have everybody walk around and like how hard is it to avoid each other versus if you're running, then then you're a lot more likely to have collisions if you're running around in a confined space. So they find each other more easily. What else happens when you're running around like that? What happens when you do hit?
That energy transfers?
It does. So anytime there's a collision, we're going to have a transfer of energy. But if you're running around and you're trying to avoid each other maybe, but if you do hit, you're more likely to hit really hard.
Yeah.
Right? You're going to have higher energy collisions. That's exactly it. Collisions have higher energy. So they have more energy, so they're more likely to be able to break a bond, and they're more frequent. The collisions just happen more frequently at high temperature because they're moving faster. Okay, so higher temperature, you have higher kinetic energy. So maybe that is where we got to with gas law in 161. Just that higher temperature, higher kinetic energy. Okay, thank you. But even those high energy collisions don't necessarily result in products forming. There can be some other requirements. So we have to have enough energy to break the bond. And that amount of energy is the activation barrier, the activation energy. So we'll usually see that written like you might have reactants going to products. And there's this barrier. So they have to get up over that barrier in order to have a reaction. But that alone doesn't explain the actual data that we find. They also need to have the correct orientation to make the chemical bonds, right? So that's going to be this one. All right, so we'll come back to that. So here's a graph where we're looking at a collection of molecules. And these are usually normalized, so we're going to normalize it to 1, so like 100% of the molecules in the sample are underneath that curve. They're represented in that curve. And the blue one is at the lower temperature, and the red line is at the higher temperature. So at those given temperatures, we have the number of particles with a specific energy, and we can think about the number of particles that have energy above that activation energy. So that's all these guys on this side. So as the temperature increases, we take that blue curve, it's a little taller, right? So this means that, for example, this number of particles are moving this fast, right? This energy, this number of particles. So we shift that curve to the higher energies, to the higher kinetic energy, higher speeds, essentially. And so you can think about the area under that curve, like here. As we shift from the blue one to the red one, more of them move into this area. So that's another way to think about how temperature affects the energy of collisions, how more particles can reach that activation energy. Okay, so let's think about what happens when we form the bond. This is called the Lennard-Jones potential. So we're looking at the 0 of energy is separated atoms. And as they get closer and closer to each other, they mutually stabilize each other. So we kind of see that with the electron density. In the case of H2, it goes from an S spherical shape to they're kind of reaching out towards each other and stabilizing each other. And eventually we get that ponding density in between the atoms. So that's really represented right at the lower, that bond distance. But it's not actually just sitting there. Of course, it's vibrating back and forth. And so we can think of that as a vibrational energy where they come close and then they go far apart. So they're kind of vibrating back and forth on that line around that lowest vibrational energy. Then up here in this picture, this is a higher vibrational energy level, right? They're coming even closer together and even farther apart. So if we were to add enough energy, right, all of this right here, the bond energy, that would take our molecule and it would give it enough energy to separate the atoms back to their individual atoms from the bond. So this is also an energy diagram. It shoots way up to infinity because they can't actually occupy the same space. So that matches the physical reality as well. Okay, so this is an energy diagram, or sometimes we will talk about as a reaction profile or an energy profile. In this case, we're looking at the internuclear distance, and it's more intuitive. It's pretty intuitive that way. But in some cases, like I don't know if you've seen one that looks like this little drawing where we have reactants, where we have the reactants going to the products. And we can think about one bond being broken and formed, for example, but it's theoretical, right? It's an abstraction, so they can be hard to visualize. So going back to the Lennard-Jones potential, we define the 0 of energy as those atoms being completely separated. And the reason this is negative, so the bond energy is defined. The energy it takes to break a bond. So bond energies are tabulated as positive values. The molecule is always more stable than the individual atoms. To go from H2 to 2H, that's going to take energy. That'll be the bond energy. So this is endothermic as written that way. Bond energies are the only ones that are defined that way. The energy it takes to break the bond, which implies that it's endothermic, even though we look up our values. It's just a confusing concept. So it's easier. This is one of those things they'll ask at the end of the chemistry series to assess the program, whether students are really getting chemistry at the end of 3 quarters. And most people get it wrong. I mean, it's really like 50%. What's more stable, H2 or the H atoms by themselves? That bond stabilizes the atoms. It stabilizes lower energy than the individual atoms. Yeah, because there's a lot of language where we talk about the energy stored in bonds. It's not actually stored in bonds, right? We can think about just saying, okay, this molecule has a certain energy by virtue of the way it's connected, and that we're just going to say, okay, here's our absolute energy. This line, this is our reactance. Whatever it is, whatever that reactant is. And it'll have different amounts of energy. For example, a larger molecule will probably have a higher energy. It depends, right? But a more negative value is lower, right? It's more stable. So the conventions can be a little bit confusing. And as we look at that stuff, I'll come back to that kind of idea.
Okay.
But generally, that's why energy diagrams are so useful. It helps you think about what's lower on that energy diagram and what's more stable. Where does that fall? We talk about energy stored in bonds when we have a combustion reaction, for example. We completely obliterate the molecule, and that releases energy. That's why we burn things, to heat stuff up. Right? So in that sense, it's kind of energy stored in the bonds. It works mentally, but it's not literally, it doesn't literally translate to our energy diagrams and the bond energy conventions. I think it's good to pin a couple things, a couple foundational concepts that you know are true, and then work things out from those. Okay, so that's an energy diagram. We're going to work with those a little bit. Here we go. This is a nice one, right? Because this is what I was thinking of earlier, this NO plus ozone. These have to have a collision that get over the barrier, and it's a relatively small barrier in this case. But they also have to have the right orientation. You can see the way it's drawn over on the left. It's oriented so that if that collision can break the ozone bond there, then it will add the oxygen over on this molecule. So this activated complex, or sometimes these are called transition states, and they're often given a little, this little dagger symbol. That's represented right here. The top of that barrier is sort of half breaking and half forming the bond. And it shows that. And then it's right up there. If it has just enough energy to break the bond and it's in the right orientation, it could go back to reactants or it could go to products. And so we'll look at the rates. How often do they go to products? That it turns out that orientation effect it really slows the rate down. It's a huge factor in there. All right.
I have a quick question. Is the energy on the y-axis in this one as well, is that representative of the bond energies in individual atoms and the reactants and products?
Yeah, so one of the things we look at, I think, in 161 is bond energies, adding up the average bond energy present in the molecule.
Yeah.
And then you do bonds broken minus bonds formed.
Yeah.
And that's different. We usually do products minus reactants, but we do bonds broken minus bonds formed because of that opposite definition of bond energy being the energy it takes, so they're automatically made positive even though they are truly endothermic. So that works, but the average bond energies, it depends on it. Those averages are calculated from a variety of molecules, so they're inherently less precise than actually measuring the energy of the reactants in this particular reaction.
Right.
Yeah, cool. Integrating some of that past knowledge. All right, so what have we got here? Sufficient energy to form the complex. That's the transition state. And if they make that energy requirement, then they've reached the activation energy. And the difference in the energy change between the reactants and products is the enthalpy. Or if we're at constant pressure, such as in a lab, that is also the heat. And I'll just write a little notation. The enthalpy at constant pressure is the heat. So you may see those interchanged a little bit. You probably saw enthalpy a little bit in 161.
Yes.
So let me go ahead and write that on this diagram here. That's going to be the difference between, in this case, we're going to do products minus reactants. So this is going to be, that's going to be heat released. So it's going to be a negative value and it's going to be exothermic. Right? Does that make sense? That's what they're asking down here. Oh, and we have values given on this energy scale. Right, here's one value. So we can look at these different values here. I'm going to draw one in. That energy barrier. So in order to go from products back to reactants, our energy in the reverse direction is going to be from that products line up over the barrier. Activation energy in the forward direction is given 10.5 kilojoules per mole. Right? Does that make sense reading the diagram? Then the reverse direction, the products are way down at minus 200 kilojoules per mole, and they have to get up over that barrier to the transition state. So that's going to be 210.5 kilojoules per mole. All right, so relative energy of the bonds, which bonds are stronger, reactants or products?
Products, I'd say.
Yeah, why is that? What's another way of saying that?
It takes more energy to go from products to reactants.
Yeah, and they're lower. They're just lower on the absolute energy. Lower energy on the diagram is more stable. Stronger bonds. So a lot of that really is about language, I think, and how to use the language in a way that doesn't confuse you more.
So if the energy is like a high positive number, it just means that it's like pretty unstable and that it's pretty easy to lose its bond.
Yeah. All right, so when the reaction occurs, does it absorb or release heat? Releases heat, and it is exothermic because it goes from high energy to low energy. Okay. So here is another energy diagram, just in general, A and B, reactants and products. And with the reaction coordinate, we're always thinking reactants towards products. And in the next chapter, we're going to talk about reactions that go both ways. So we'll just assume it's written in a particular direction. In this case, A goes to B. So in the forward direction, that energy barrier corresponds to number 3. In the reverse direction, that'll be 2. And the enthalpy
1.
will be 1. And is it endothermic or exothermic?
Endo.
Yeah. So it had to absorb energy to get up to that. It's endothermic. Okay, so the number of collisions with energy greater than the activation energy, is given by an exponential. E to the minus EA over RT, where R is our gas law constant and T is the temperature, in Kelvin, of course. So that represents, that's that graph we saw, that represents the leading tails of that curve, the ones that are above the EA. But the actual reaction rates are much lower than just that fraction of particles. And that's where we get the orientation coming in. So here we go. This is what I was thinking of, this nice diagram showing that when they collide in the oxygen to oxygen direction, they just bounce off each other.
Yeah.
Or if they break a bond, then the original bonds reform. So they don't go to products. It's not a productive collision. When they collide in the right direction, though, then they can form products. And that happens a lot less often. So we introduce what's called the frequency factor, A, right? That's going to turn out to be a constant of integration. It's just a value. And we could quantify it for a given system, but it is empirical. It's something that we observe. And so it's not built into our theories because it's not something we calculate from first principles. So here are those two requirements that I kind of started with. They have to have enough energy to reach your activation energy, and they have to have the correct orientation. And so that is A, that's our frequency factor. And we can break that down into counting how many collisions happen, and then this steric factor that has to do with the shape of the molecule and how open it is at that point where it has that collision. But we're just going to lump them all together. Right, so we could break it down further, and there's lots of work doing this where people were looking for ways that we could make predictions, but it's pretty empirical. Here, we're going to work with this equation, right? We could take the natural log of both sides, which is always fun. We love to do that. That's going to get rid of the exponent, right? The natural log of E is, or I'll just say e to the x is x. So when we take the log of both sides, we get the log of k is minus EA over RT plus log of A, that frequency factor. So again, we have something that we can easily map onto the equation of a line. Oh, it's time. All right. See, I get so excited. I love this stuff. So have a great afternoon.